Marhaba. Okay, today we want to talk about combinations. Again, combinations are objects we've seen before. They are just subsets, but we want to give them special names in this setting of combinatorics. Okay, so remember we talked about permutations in previous sessions, where a permutation is a sequence of length k of distinct elements chosen from a set containing n elements, say. Okay. Now, and by a sequence means that it's an ordered list of elements, an ordered arrangement. So we care about order. In combinations, we don't care about order. We just want to look at a collection of elements. So let me elaborate. Suppose we have 4 students. Let's start by an example. Suppose we have 4 students. Let's call them A, B, C, and D. And we want to choose a group of these students. So choose a group of 3 students from these students. Choose a group of 3 students. And let's see in how many ways we can choose these 3 students out from ABC, from the students A, B, C, D. Okay. So suppose we want to form a group, and this group will represent the class. So for example, we can choose the student A and B and C. So we can choose this group, or which group? We can choose A, B, and D. Here's a second group. What else? We can choose B, C, D. Right? We can choose these 3 students, B, C, D, out of A, B, C, D. And we can choose A, C, D. Right? A, C, and D. And I think these are the 4 possibilities. ABC, ABD, BCD, and ACD. Okay, so in total we have 4 choices to choose from, 4 different groups of, okay, or each containing 3 students, each containing 3 students. Okay. Now again, this will be a combination. So what is ABC in mathematics here? How can we represent this? Simply, it's a set containing 3 elements. The 3 elements are A, B, C. And remember that in a set, we don't care about the order. We just care about who are the members of our set. So remember, ABC is the same set as BCA, right? In sets, we don't care about order, so we can represent this group of 3 students as a subset of the set containing the 4 students, and this subset contains 3 students. So now what is this group? This is the subset containing ABD, right? And this is the subset containing ACD, okay, and this is the subset containing BCD. So we can represent our groups by subsets. Okay, this example motivates the idea of a combination. So what is a combination? Simply a K combination. So these are 3 combinations. So a K combination, okay, of a set S, say, of a set S, is simply a subset of S of cardinality or of size K. So maybe it's a fancy name, but what is a K combination? It's simply a subset which contains K elements. Okay, like this is the subset S, and these are the 4 examples of 3 combinations. Okay, why they are 3 combinations? Because they are subsets of S, and they contain each one of them contains exactly 3 elements. Okay, so now the number of K combinations of a set containing n elements is denoted by NCK. Okay, so here let's define NCK, or if you want CNK, is the number of K combinations of a set containing n elements. Okay, so which means, again, let's break down or unfold this definition. What is a K? So NCK is the number. Okay, so this is NCK is the number of subsets. Of subsets of size K of a set of containing n elements. So you look at a set of which has n elements, write down all the subsets which has K, each of them has K elements, and the number of these subsets is called or denoted by NCK. So for example, here, what is this number for? This is n is the size of the set, so here we have 4. Now we listed all subsets of size 3, so here K is 3, and we found there are 4 of them, 1, 2, 3, 4. So 4C3 is equal to 4. Okay. Now in a similar fashion, how do you compute a 4C2? Okay, so let's compute 4C2. Okay, so what is this number? So what is it? This is the number of subsets of size 2 from a set containing 4 elements. So let's say here is a set S, say, of 4 elements, 1, 2, 3, and 4. And now we want to list down all the subsets of S of size 2. So here is the first set, 1 and 2. This is a subset of S, right? Every element here is an element here. Here's the second one, 1, 3. Here's the third one, 1 and 4. Okay, here's the fourth one, 2 and 3. Notice I will not list 2 and 1 because 2 and 1 is the same as this subset. We don't care about the order. And this is 2 and 4. And the final one is 3 and 4. Okay, so 4 and 2 is not a new collection. It's not a new subset because it's here. Okay, so we only have 6 of them. So this means that 4C2, the number of subsets of a set containing 4 elements, each of them has size 2. Okay, let me say it again. The number of subsets of size 2 from a set containing 4 elements is 6, right? 1, 2, 3, 4, 5, and 6 such subsets. Okay. Now let's find a formula. Okay, so we want to find the formula for, okay, I'll tell you the formula and then we prove it. Okay, so NCK, the number of subsets of size K from a set containing n elements, is equal to n factorial divided by n minus k factorial. Notice until now, what is this number? This is NPK, the number of K permutations. But we still need to divide by one more number, K factorial. Okay, so from where did we get this formula? This is NCK. Okay, if you want, try it here. 4C2 is equal to 4 factorial divided by 4 minus 2, 2 factorial by K factorial, which is 2 factorial, and this is 4 times 3 divided by 2, and this is 6. Okay, so let me tell you how we do this. So suppose we start with a set of n elements, A1, A2, up to AN. Now what's NCK? It is the number of subsets of size K. So suppose this is a subset of size k. Let's say it contains the elements x1, x2 up to xn, where each xi is one of the ai's. Okay, so this is, sorry, not xn, this is xk. So we need a subset of size k, and this is a subset of S. So x1 could be a4, x2 could be a1, and so on. So say this is the first subset. Let's choose another subset, y1, y2, up to yk, right? This is another subset of size k. Anyway, we keep doing this until we list all of the subsets of size k. I don't know, let's say the last one is z1, z2, up to zk. Now, concentrate on one subset of size k. From this subset of size k, we can form a permutation of length k. So what are the permutations? They are sequences of distinct elements from here. So look, we can say this is the first one, x1, x2, up to xk. Or we can say x2, x3, x1, up to xk, and so on. We list all permutations, k permutations. Okay, so here, I don't know, xk, x1, I don't know, but x4, say the last one. Anyway, so you list all the permutations of length k which use these elements. Okay, so how many permutations there, so these are k permutations. These are k permutations from a set containing k elements. So the number of these are npk and but here, the kpk, right? We are looking at k permutations from a set containing k elements. So this is npk, and we know that this number is k factorial. But notice that every k permutation here is also a k permutation of this one, of S, right? Because the elements here are elements here, and this is a subset of S, and so on. Now, if you look here as well, you list all the k permutations from this set. So say y1, y3, y2, and so on. So again, here we are looking at k permutations from a subset containing k elements. So here again, we have k factorial many. And here we have k factorial many. And in the same way, we have k factorial many k permutations. Now, all the permutations here, together with all the k permutations here, together with all the k permutations here, are all the k permutations of S. Okay, so this means that what are the k permutations of S? S contains n elements. So the total number of them is npk. But what is this number? This number is the number, okay, what is this one? This one, and this one, and this one, all of them, these are all the k combinations, right? These are all the subsets of size k. So it's equal to the number of k combinations. And since for each combination we have k factorial many k permutations, then we just multiply this by k factorial. Okay? So in other words, the number of k permutations, the number of sequences of length k of distinct elements is equal to the number of subsets of size k of a set containing n elements times k factorial. Now if you divide by k factorial, you get so therefore nck is equal to npk divided by k factorial, but npk is n factorial divided by n minus k factorial times k factorial. Okay. And this is the formula for nck, n factorial divided by n minus k factorial divided by k factorial. Okay, now let's So again, just to avoid any confusion, what's NCK? This is the number of K combinations, but a K combination is a subset of size K. So the number of subsets of size K of a set of size n, of a set of size n. Okay, so let's have examples. Now, first example. Suppose we have 15 people, okay, and we want in how many ways we can form a football team. So form a football team from these 15 people. Okay, notice that how do we form a football team? We need 11 players. So all what we want is choose 11 players from the 15 people. Which means if you choose 11 players, this is a subset of the 15 people of size 11. So this means the number of football teams is simply 5 choose 11. What is this number? This is the number of subsets of size 11 from the 15 people. Each subset will represent a football team. So this is 15 factorial divided by 15 minus 11, which is 4 factorial, divided by k factorial, which is 11 factorial, and this is 15 times 14 times 13 times 12 divided by 4 factorial, 4 times 3 times 2 times 1, so this is 4 times 3 is 12, and divide by 2, this is 7, so 15 times 7 times 13 is the number of different ways we can choose 11 players out of 15 people. Okay, so now look at this question. How many binary strings of length 5? How many binary strings of length 5 contain exactly 3 ones? Contain exactly 3 ones. Okay, so I'm looking at binary strings of this form. So 1 0 0 1 1. See, it's of length 5 and it contains 3 ones. You can look at this one as well, or this one, okay, or this one. So every one of these are binary strings of length 5 containing exactly 3 ones. So how to know this number? How many are there? So think of, so our mission is to form such a number, and we want to divide this mission into tasks. So I'll tell you what is the first task, is choose 3 digits out of the 5 digits. Out of the 5, right? We have 5 digits. 1, 2, 3, 4, and 5. We need to fill them with zeros or ones. So first step, choose 3 digits out of the 5 digits. 5 digits, and fill them with ones. And fill them with ones. So, for example, suppose we choose the first, the third, and the fifth. So we choose them, and then we fill them with ones. Okay, 1, 1, and 1. What is the second step then in our mission? What's the second task is fill the rest with zeros. The rest digits with zeros, right? Because if you fill the remaining two with zeros, then we get one of the desired binary strings of length 5 containing 3 zeros. 3 ones. So it remains to see in how many ways we can do step 1 and in how many ways we can do step 2. So notice that I am following the product rule. So this means in how many ways you can choose 3 digits out of 5 digits. So this is exactly the same number of ways that you can choose subsets of size 3 from a set containing 5 elements. So here our set contains, say, first digit, second digit, third digit, fourth digit, and fifth digit. So this is the set S, and we need to choose a subset of it of 3 elements. So here, for example, the red ones, we chose the first, the third, and the fifth. So in how many ways we can choose subsets of size 3 from a set of size 5? This is 5 choose 3. Okay, so this is the number of ways of choosing 3 elements out of 5 elements, or 3 digits out of 5 digits. Now, in how many ways we can fill the remaining digits with zeros? Okay, we only have one way, just put zeros. So this means that the total number of such strings is this number times 1, so which is this number, 5. Okay, 5 choose 3, which is 5 factorial, divided by 5 minus 3, which is 2 factorial, 5 minus 3 factorial times 3 factorial, and this is 5 times 4 divided by 2, I divided by the 3 factorial, and this is 10. So there are 10 of these strings. Find the rest. Okay. Let's have one more example. Okay, suppose we are in a university where we have the following. We have here the math department, and here we have the computer science department. In the math department, there are 9 faculty members. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are the faculty. We have 9 faculty, and in the CS, we have 11. Okay, so here are 11 faculty, and we are asked to form a committee from the 2 departments. We want to form a committee, and the committee consists of 3 people. Okay, let's choose red for the CS. We need to choose 3 people from the math and 4 from the CS. Okay, so we need to choose a committee. There are 3 people from mathematics department and 4 people from the computer science department. So in how many ways we can choose such a committee? Well, again, we break our mission into 2 steps. The first step is what? Choose 3 math professors. In the second step, choose the 4 computer science professors. And it remains to see in how many ways we can accomplish the first task. Well, what is the first task? We need to choose 3 math professors, which means choose 3 professors from a set containing 9 elements. In how many ways you can do this? This is the number of subsets of size 3 from a set of size 9. And so we know this number is 9 choose 3. And this number is, we have 11 CS professors, and we need to choose 4 of them. And now the total number to form the committee is the number of ways in step 1 times the number of ways in step 2. This is by the product rule, so nC3 times 11C4, and this is equal to n factorial divided by n minus 3, which is 6 factorial times 3 factorial times, again, 11 factorial divided by 11 minus 4 factorial, which is 7 factorial divided by 4 factorial. Okay, so you get this number, and this number is huge. You have 27,720 ways to form a committee, to form such committee. Okay. Okay, let me finish with this outstanding observation. Look, what is n? Okay, so let n be a positive integer. And imagine n is a size of a set. So suppose we have a set S which contains a1, a2 up to n elements. What is the number nc0? So this is the number of subsets of size 0 from the set S, and this is 1 because we only have one subset of size 0, namely the empty set. Now suppose we add this number to nc1. What is this? This is the number of subsets of size 1 from the set S, and notice this number should be n because we have n many subsets of size 1, namely this is the first subset of size, this is the second, and this is the nth one. Okay, so we have, this is 1, this is n, plus nc2. What is nc2? It is the number of subsets of size 2 from S. Suppose we keep doing this until we exhaust all subsets. So this means that the last one, this is the number of subsets of size n from S. What is ncn? It should be 1 because there's only one subset of size n, which is S itself. Okay, notice what is this? Is the what is this? This is the number of subsets of size 0, the number of plus the number of subsets of size 1 plus the number of subsets of size 2 up to including all subsets. So this is the number of all subsets. But we know this number, this is the cardinality of the power set of S. We know this number is 2 to the n. Okay, so I think this is a very nice magical formula. So if you sum nc0 plus ncn, so try it for n equals to 4. Okay, so if you sum 4c0 plus 4c1 plus 4c2 plus 4c4, you should get 2 to the 4, which is 16.